25, I don't remember. Go! Or should we blow that off and just, you're good at that, you don't need it, we should just go to the lesson.
Warm up.
You need to warm up?
Why are these wrong?
I didn't know they had that.
I can't remember. 6 for 6 and 7 different or typical load path.
What?
What does that mean? Oh.
Yeah, that's what I wanted to say.
What does that mean?
Well, you'll understand when you read the book. So, it makes sense after the lesson. Don't worry.
So this is for, say, and you're saying.
6 and 7, the question is the one generator.
Oh, okay, so you're saying that this
the
statement applies to 6 and
right,
7.
the directions for 6 and 7 are 4 related.
Oh, no.
Do I have a reason for a martial art? No. Did you feel something mean? No. Okay, so yes. let's do it. Epsilon over 8? All right, all right. Boom. Now that you guys are getting good, we should have a little racy race, huh? And da, 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 8. All right, sorry, second, get my coffee. Boom, we good? Cool. All right, today's your start of Calc 2, and like all starts of classes, it's all easy and a lot of vocabulary. So you will find these next few lessons pretty straightforward, I hope. Okay, sequences. What's a sequence? Am I recording this? Am I recording? Oh, yeah. Yeah, it's recording. Okay. Sequence, what is it? Just plain old, I'm gonna be a fancy, mathy way. Just tell me, what do you think a sequence is? A list of numbers. I like it. That's a good start. Although I guess it could be random, it usually in math anyway follows a pattern. You do such things as random number generators, but you don't usually randomly generate a list of numbers. An example, 1, 2, the first sequence you ever learned is that one. Actually, it was probably finite. That's a finite sequence. It's a list of numbers following a pattern, and it ends. You could, I suppose, go -1, -2, -3, -4, forever. That's a finite sequence. Following a pattern. Is a sequence the same as a series? Do you remember what a series is? Okay. Now multiply. Good try. Try again. A series is to add. Is the, let's just say the sum. The sum of a sequence. Okay, it also follows a pattern, but rather than just crank out a bunch of terms, you add them. Now at that point you might think, what? You have to be a real math nerd, who cares? Well, like a lot of math ideas, that seemingly useless idea is huge. When I make payments on my loan, that's a series, a finite geometric series. So series actually are very applicable to real life. Notations, by far the most common notation is terms are named with an A and a subscript. To denote the term number. Term number. So A sub n means nth term. 3n. Okay, this, the general term is the rule that makes all terms. The book calls it generator form, but I have never seen that in any other textbook. It's always called the general term. All right. So if I ask for a sub 1, obviously that means the first term in the sequence. A sub 2 means the second term in the sequence. Sequences versus functions, because this is a rule that makes terms. It's like a function. It does something and spits out an output. And so sequences or functions are both similar because they both involve using a rule that gives outputs from an input. They are different, however, in what goes in. If I were to look at y equal 2x, then x is all real numbers. And I could throw them out in any order I like. But if I said the corresponding sequence to that would be the nth term is 2n. So instead of when x is 1, y is 2, I'm saying when the nth term, or the 1th term, or the first term is 2, the n is only whole. N increases by 1 each time. We typically go in order, right? X and Y could jump wherever I want. I could go 3 to negative 3 to 5 to negative 17.24. Who cares? But when you go to sequence, you don't go from 3rd term to 5th term to 7th term. You go in order. First term, second term, third term. So n equals 1, n equals 2, n equals 3. Because of that, because n is only whole, sequence graphs are not continuous. They're not connect the dots. They're more like the first term is 1. The second term is 2. The third term is 3. And you do not connect the dots, because if you were to connect the dots, you would be saying, hey, buddy boy, the 1.3th term is, well, that's stupid. There's no such thing as the 1.3th term. Right? Right, Mr. Rickman, I agree, 100%. All right. Bounded. Bounded we don't usually use with functions. Although, actually we do. Upper bound, lower bound, love in the glove. Do you guys remember the love in the glove from Trinity? Least upper bound and greatest lower bound? Could you find, if I asked you for the least upper bound of this polynomial, could you?
We never learned.
Yes, you did. I know Miss Cannon taught you the love in the glove. She might not have called it the love in the glove. That's not universal. That's me. Crazy. But she taught you that. Okay. Whatever. Not a big deal. Don't worry about it. A sequence is bounded above if there is some number that all terms are less than. Another way to say it more wordy is there is an L such that L for limit, all terms, which are a sub n, are less than or equal to that upper bound. Bounded above means there is an upper ceiling on all the terms. Ayat? I'm not sure what ayat means. I'm tired. All right, are you with me? Bounded below. Bounded below would mean there is an L or lower limit such that all terms are above that floor. All terms are greater than or equal to that limit. You know, the last part there is a little like limits. You say you can have a left-hand limit, a right-hand limit, and the limit. Well, same goes with bounded. You could have bounded below and bounded above, but then you have bounded. A sequence is bounded if it is bounded above and below. Could you give me a sequence that is bounded above and below? It would have a top and a bottom floor. Bottom floor and top roof. Give me a function, but in sequence form, that has limitations on it above and below. So you could say something like that's bounded, right? Things that have horizontal asymptotes, they're often bounded. Monotonic means the sequence doesn't actually have to be a sequence. You will hear functions called monotonic. If a function is called monotonic, then that really refers to the derivative being one sign. And if the derivative is one sign, then the function must always be increasing or always decreasing. So monotonic means one sign, but it really means the sequence is always increasing or decreasing. It doesn't mean the terms are always one sign. They could be, actually, it probably means that. No, they wouldn't have to. So the sequence is always increasing or decreasing. All right. You follow? All right, then. One of the skills you need to be able to do is, given the general term, find specific terms. So here, I'm giving you the general term, or the rule that makes terms. And if they don't specify, assume that n starts with 1, unless they otherwise specify. So for example, in this sequence, I want the first 4 terms. Well, what is a sub 1? If you put in an n of 1, what comes out? Negative 2. If you then put in an n of 2 for the second term, a sub 2 is negative or positive 4? Positive 4, because now you have a negative to an even power. Okay, then negative 6, then positive 8. Now, if you were to graph that, which it says in the directions part 2, let's go to 1, 2, 3, let's go to 1, 4 in the x, and I think you'll agree that we'll need to go up to 8 or so. In the y. When you graph sequences, the number of the term is the independent variable, and the term that's spit out at that point is the dependent variable. And you don't start at the origin, you say the first term, term 1, is negative 2, and you put a dot, and you do not connect as you go. The second term is positive 4. The third term is negative 6. The fourth term is negative 8. All right. Do you reckon this sequence is bounded above and below? Is it bounded above and below? Or no, it will go forever big and up and down. Yeah, so it is not bounded above, below, or gently. Will you do the other 3, please? All right, does your work look something like that? Or not? Okay. We said the first one is not bounded above or below. Is the second one bounded? It is. It's bounded below and above, so it is bounded. The third one, is it bounded? Bounded. It is. What's the lower? You could give me, I said it's bounded below if there is some number that's less than all numbers. What's less than or equal to? What's a possible number that is the lower bound for this? 1/2 is lower bound. 0 would also be a lower bound because all terms are above 0 as well. 1/2 would be the least upper bound, or the greatest lower bound, rather, sorry. Is it bounded above? What is it bounded above by? 1. It's bounded above by 1, yeah. So it's bounded. What about the last one? Is it bounded? Yes. What's the lower bound? -1. What's the upper bound? 1/2. And now let's talk about what happens as we go on. Now, if you think about how big a word increasing is to calc 1, that's how big a word converging is to calc 2. Converging is a granddaddy. Which of the following sequence approach a limit as n goes to infinity? Do the terms approach a certain y value here, or no, they spiral out of control? Spiral out of control. So there's no limit to the terms. The terms don't approach one outcome. So this is a no. B, do the terms approach a limit? Do the terms approach a limit? Here, you tell me. Listen to the sequence. 0, 0, 0, 0, 0, 0, 0. What do they approach? 0. Is there a limit? Yeah, there's a limit. Okay? Yes. C. What are those approaching? Or do those approach a limit?
1.
Yeah, they approach a limit, so that's a yes. 1. Bye. Good luck. And is that bothering you?
Thank you.
Oh, gotcha. Right on. I hear you. Okay, and you guys will win because you're the last period. D, yes or no, approach a limit? Yeah, they do approach 0. They approach 0. All right. Now, converges then is the idea that they do approach a limit. If the terms start to approach a number, then the sequence converges. Diverges does not mean goes to infinity. Diverges means fails to converge. Okay? People say sometimes the wrong thing, and they say, "Oh, it diverges, so it's infinite." That's not necessarily true. If it's infinite, it diverges, but if it diverges, it's not necessarily infinite. All right? Let me give you an example or two here. If I ask you, and this is a very common problem, does the sequence converge or not? Do the terms in this list start to approach a number? To do that, you will not just say, yeah, it goes to, or no, it goes to infinity, so that, no. You will, to prove this, you will show the infinite limit equals a number or not. So if I want to say, does that first sequence converge, I take the infinite limit of that. What do those terms approach? As n gets infinitely large, log of n, yeah, wouldn't it get, it keeps going up, right? Doesn't it get infinitely large? And so we would conclude diverges, because L is a numerical, an actual numerical value. Infinity is not a numerical value, okay? That's what I would like you to show each time. just so we're clear, you're giving me two things. Does it converge or diverge, and what's the evidence? What are the two reasons Norma doesn't exist in calculus? Oscillating and left-hand, right-hand limits are not the same. So in this case, it does not exist because of oscillation. Because it fails to converge, it diverges. How do we do? Oh, don't worry. Oh, sorry. We? Oh, no. Okay, so did you get diverge, diverge, converge, converge? Okay, cool. That's the more fun part is pattern recognition. You're mathy people, whether you say it or not. And pattern recognition or seeing patterns and things is just part of your DNA. So you're going to love it. Okay? Now, there are lots of different patterns to be found. And your goal will be to write a rule for them. So instead of being given the general term and you write the first four, they'll give you the first four and you write the pattern, the general rule. There are a couple. I probably should have started with even. Back in the day, how could you take whole number inputs and spit out only even number outputs? Times 2, yeah. If you take whatever they put in, which is n, and double it, you'll always get an even number, assuming that what they put in is a whole number, which that will be the case. They will only be putting in wholes. If you get two n's by, or evens by doing 2n, then you get odd by 2n plus 1 or 2n minus 1, whichever you prefer. Okay? So with that, then, if I were to write the general term for this sequence, I would say generally the nth term can be found by. So yeah, let's try, say you tried 2n plus 1. Would you write yourself a note? Always check. You should always check after you write a rule that your rule works for at least 2 terms. So if n equals 1, you're supposed to start with n equals 1. If n equals 1, does my rule work? No, I get a 3, so that's not working. 2n minus 1, I heard. If n equals 1, what do you get? 1. If n equals 2, what do you get? 3. Is it working? Yeah. Okay. Alternating negative. You'll often see an alternating sign there. That's super duper important in Calc 2, alternating negative, and there are typically 2 ways to do this. One is -1 to an exponent of n. And because that n will go back and forth between even and odd, the whole result will go back and forth between positive and negative. Sometimes you will start started that off by 1, either -1 to the n plus 1 or -1, depending on if they wanted you to start even or positive or negative. You might tweak that exponent a little so it starts positive or negative. Rarely, but once in a while, you'll see this used for when teachers are trying to make you think a little bit. Cosine of pi n Wouldn't you agree that that would go between cosine of pi, which is negative, cosine of 2 pi, which is positive, cosine of 3 pi, which is negative, 4 pi is positive. So that's another way of alternating. But that is used less than this. Would you do number 2, please? Would you write the rule for number 2, general term? Ready? Or not yet? You should know if you did it right or not. You have a way to check. So what's your rule? 2 times negative 1 to the n plus 1. What if choice B was 2 times negative 1 to the n minus 1? Does that work? Yes. What if somebody did negative 2 times negative 1 to the n? Does that work? When n equals 1, you would get a positive 2. When n equals 2, you get a negative 2. Does it work? Yeah, it works. So there are a lot of ways to get there. You need to, obviously, in a multiple choice setting, be able to discern which one doesn't work. Let's go to the next idea of arithmetic. Let's do the old, what do you call those? What do you call those when you say this is to this, is that is to that? Is that what a syllogism is? Syllogism is a 3-step logical argument. That's a analogy? Okay. So, consider this analogy. Arithmetic is to linear as geometric is to exponential, okay? These are sequence terms, but they have brothers in function ideas. When you do arithmetic, you're really doing a constant rate of growth. If you, for example, were supposed to look at the table of this, the first term is 9, the second term is 15, the third term is 21. Aren't you seeing a constant rate of change? Up 1 over up 6, up 1, up 6, up 1, up 6. If it's always adding the same constant, it is linear and arithmetic. Now, just like y equals mx plus b, we're going to have a corresponding version here. It'll be a1, but instead of starting with the xy kind of thing, we start with the b, the first term. We say the first term is this, and we're adding something which we'll call a common difference oh so many times. So in this case, for example, you could say the nth term would be just to start at the baseline of 9 and add, what are we adding each time? 6 and minus 1 times. Follow? All right. Jump to, or try the next one on your own. Try the next one on your own, please. There are lots of different sequences, arithmetic, geometric, but there are infinitely more than that. Those are just 2 important ones, but not the only ones. Right? What's the rule? A sub n equals? Not yet. They look like squares. Is it a sub n equals n squared? Does not work. So, what's the rule? N plus 1 squared. Does that work? Okay. P metric is tantamount to exponential because instead of adding the same thing over and over again, which can be shortened by just saying the thing multiplied so many times, you're multiplying by over and over again, which can be shortened to an exponent. So instead of y equals some starting number times a constant to a power, you're going to be looking at more like some starting number times a common ratio to a power. Now we don't start at 0, we typically start at 1 here, so that's what I should. So, say this guy. What are you multiplying by each time? Oops. Did I do this wrong? Yes, that's not what I intended. Is this what you have?
No.
That's why I changed it. Sorry. That's not geometric. What is your sequence? Sorry. Okay. All right. Are you multiplying by the same thing over and over again? What are you multiplying by? -3. So write the rule for me. And your rule? -2 times -3 to the n minus 1. True that. Okay, and you check it and it works? Would you write the pattern for the next one, please? The point being that sometimes there are multiple patterns that you have to analyze. You could write that in 2 or 3, depending on your how you look at things. Okay? What's going on up top? Describe the pattern. +2, right? Or preferably linear or arithmetic. Okay, so what is the top pattern? 5 plus 2, some number of times, yeah? And I believe that checks. Yeah, that works. Okay. What about the bottom? Let's just do the bottom, not include the sign. What about the bottom? 4 times 2 to the n minus 1. Okay. The only thing we haven't accounted for is the sign. So how do we get that alternating negative? -1 to the n minus 1. That would start positive, so we're good to go. Could you possibly lump that -1 in with the 2 because they have the same power and call it -2 to the n minus 1? Would that be okay? It would be. All right. Last but not least, the last sequence. Try and write the formula for that. Okay, that's me. Don't try and write a formula for that because you can't do it. Instead, try and analyze the pattern in that and tell me what the pattern is. If you are a mathy person, then you probably know that. But don't tell the others and see if they can figure out what's the pattern. There is a pattern for those numbers. Got it? Okay, what's the pattern? You find the next number by Adding the previous, all of them, or one of them, or adding what? Previous two terms. So, 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8, the next one would be 13. What is this sequence? This is the most famous sequence in all of mathematics. Nobody? Fibonacci. Yeah. It is the most famous sequence in all of mathematics. Now, pause for a second. Let's nerd out a little at the bottom, and this is going to blow your mind. Are you ready to have your mind blown?
Yes.
Okay, this will be short, and I'll try and I got so carried away. I was so pumped up I couldn't even keep my thoughts straight in last class. I took a whole class on Fibonacci. This is awesome. All right, so that, first of all, that's a recursive sequence, and that means that to know the next term, you have to know the one before it. You can't write a formula that goes all the way back to A1. You have to know the one before it. That's recursive. Would you please, just for the fun of it, let's start by drawing squares. Would you draw a little 1 by 1 square? And if you can, write a 1 in it. Then, just to the right of that, draw another 1 by 1 square. We're going to show Fibonacci in a visual way. Now, if I were to add those two lengths together, I could get a new square of 2 by. Right? Just above that. Now, just to the left of those, I'm going to add 2 and 1 and get a 3 by 3 square. Now, it might seem weird, but just below that, would you make a square like that? I know it feels like you should build off the 3 and the 2, but instead, put it below. Okay, so it is still 3 by 2. 3 plus 1 is 5. Now, to the right of that guy, let's go a square. If I build a square off that, it would be 5 by 1 by 2, or 8. If I then did another one, 8 plus 2 plus 3 is 13. Okay, and then I could continue. 13 plus 8 is 21. If I had enough room over here, boom. Okay, now that is cool, but it looks like a just jumble of boxes. Now, here's what I'd like you to do. Take your pencil, and we're going to draw diagonals through boxes. If I start at the very inside of the first box and drew a diagonal, then I pick up where I left off and draw another diagonal through the second little box, up like that. Then, from that corner, you draw a diagonal through the 2. Then from that diagonal, you draw that box, you draw a diagonal through the 3. Then through the 5. Then through the 8. Then through the 13. Then through the 21. You start to get what in real life would be a shell, a nautilus. Any shell has a Fibonacci sequence. Now, better than that, or in addition to that, is if you look at, what's that fruit, the vegetable you peel the leaves off of? Artichoke. If you look at how the leaves of an artichoke are made, it happens in a Fibonacci spiral. Okay? If you look at an acorn, they follow a Fibonacci spiral. This happens in life all the time. Now, let's talk a tree. Now, this is an oak tree, but there is such a thing called botanical mathematics. That's a field. That's something you get a doctorate in. Okay? The math of biology, or plants specifically. Okay? This is an oak tree. And this tree had a diameter of 21. Okay? Now, if you've ever looked at a tree, you know that once it branches off, it doesn't have, the branches aren't the same thickness as the trunk was. The branches get thinner. If you were to look at the diameters of those branches, the diameters of those branches would actually add to the original trunk. But they don't branch off, at least not the perfect oak tree anyway, or typically if you average them all, doesn't branch off in a perfectly equal two branches. One will be thicker than the other. In this case, then, a typical oak tree would go 8 centimeters or in a proportional kind of way. 13. Now, after another sequence of time, equal sequence of time, after every equal sequence of time, it then starts to say, all right, time to send off another branch. When it decides to send off another branch, the thicker of the two will branch off. So at stage 2, the thicker is this guy on the right, so it's going to split off. Now its width was 13, so now it's going to split off, and its 2 branches will also add to its previous thickness. So if it was 13 before, its 2 new branches will be 5 and 8. Those 2 new add to the previous one, so it's Fibonacci in reverse. Instead of 5 and 8 coming together to be 13, it's 8 splitting off into 5 and 8. After that, then, they all start to split off, but at every level, then, the branch splits off into 2 others that add to it. So if you were to look at the sums or the thicknesses of all these, 21 is the thickest, 13, then 8, then 5, then 3, then 2, then 1 is the thickest. It would form a Fibonacci kind of sequence. Now, that's pretty cool. The thicknesses are also Fibonacci. But the other thing on this is it's two-dimensional. Obviously, this tree is two-dimensional. It's flat on a page. But true trees grow off in every direction, right? Now, when a tree, if you look at it from above, when it decides how am I going to split, it doesn't do it randomly. The tree decides to send off the next branch in a way that will maximize how much sunlight it gets. And the direction it decides to go next is a Fibonacci spiral. If you look at it from above, where it sends its next branch is a Fibonacci sequence as well. Last but not least, and I'm talking, this is just really cutting it down. Let's talk about art, okay? If you look at, keep going here, 34, 65, 99, feels like that's good. Okay, check this out. If I look at the ratio of terms to the one before it, I don't know if you guys have learned this or not before. We'll see. The ratio here is 1.615. The ratio here of 34 to 21. In a Fibonacci sequence, if you look at the terms ratios, they start to approach a limit. 65 divided by 34, oops, 60, did I add that? That's 55, isn't it? Dum-dum. 55 divided by 34, 1 point, did I add that wrong? That's right, right? Okay. 1 point, oh, I looked at the wrong line. So 1.617. They're starting to approach a number, right? Like 1.61. Now, normally in math, if we see, does anybody know what that number is? The most famous number in all of art. It's not even. It's, oh, you're right. Phi. It's the golden ratio. Phi is the golden ratio. So your finger, golden ratio. It's the difference between your eyes and the top of your head, golden ratio. 8 different proportions of your body, golden ratio. All of Da Vinci's work, golden ratio. Half of trees, architecture, golden ratio. Gosh, darn it, I need 5 more minutes. I should have dumped the warm-up. I knew it.